say very simple things. Before I start, I want to thank Professor Srikanth and Professor Sandeep especially, and other local organizers for doing such a terrific job in organizing this conference and all the logistics that were involved with it. I also want to thank all the speakers who came, took time off from very busy schedules and prepared very hard for giving us this delightful series of lectures. And especially, I'm also very glad that we had the opportunity of seeing how various parts of analysis and geometry fit together. It seemed like the lectures were just fitting in a very seamless way with each other. So you got some sort of global picture. And I hope many of the students who also need to be thanked for their patience, I hope they were very much benefited by this lecture. So thank you, all of you. Okay, so I wanted to say a few words about the HSV spaces and a few words about the Strictheart system. So I had promised during the July workshop that I would prove the Strictheart system. We never got around to proving it. So maybe this gives me a chance to prove the Strictheart estimate in at least one simple case, which was actually written down on the board in the last lecture. But before that, I just want to remind you. What was the motivation for these HSV spaces, and this was this theorem of Polan and myself. The theorem. So this is. This is not yet it's not yet published or anything, but there is the working there. And the result is that you have a map from R2 into R3, and so this is the Gallen-Bertian, and here you have 2x dy. So this is the cross product. So it's R cross R2 cross R3. So here we have P psi, and psi is equal to x, y. So therefore, you see here that this is the cross product, and you have initial data, that is u and u naught, and u p at x0 is u1. And what is, as I pointed out, the energy critical space is H1. And if you do not have local existence in time in H1, in U0 and H1, you cannot do anything with this problem. So, so the classical result is that if data is in H2 and higher, H2, this is in H2 plus epsilon, and this is in H1 plus epsilon of R2. And then there is some machine that does local existence, and it doesn't matter what this structure is. You can completely ignore it. But if you want to get down to H1 critical, you really have to make use of the special structure on the right-hand side. This is what is called a null form. So the null forms that appear for the wave maps, where I explained to you that it is the mod grad U square in the Minkowski metric, they have many applications in physics, and that is this great interest of the people who are doing hyperbolic equations like Kleinemann and Tau and others to actually prove that existence.
US, what UI, just the cross product?
It's a regular cross product. Okay. And so the theorem is that given U naught in HS of R2 and U1 is HS minus 1 of R2, that S is bigger than 3/2. So we are half a derivative away from criticality. There exists a time T0, okay, such that the Cauchy problem is well posed. So that means there's existence, uniqueness, and continuous as a unique solution. As a unique okay. So this is the theorem, and we are half a derivative away, and it gets progressively harder as you move towards the criticality, because there is something that you have to So the question is that, so let me remind you very briefly that this equation, the static equation, is the mean curvature equation, which was investigated a lot by Henry Vente. And so this is this equation. Okay. And this already is a very remarkable equation because
so what is space of the solution states?
Yeah, that is HSP. Yeah. So that I'll have to define for that. Yeah. So now, but this is the regular space. This is a regular Sobolev space, but in space-time it is in HSP. Your data is measured in regular Sobolev space, but your solution is taking on values in HSP. So, for example, if U is in H dot 1, okay, this thing here, as you know, this is an L2, this is an L2, so this is just L1. Okay. Now you know that if you take in R2, you know that if your right hand side is this in L1, then an estimate of this type is false, right? Because you can just take this to be the Dirac mass, and then U is going to be just the Green's function. Okay. So X here is X1. So if you have the right hand side in L1, you do not expect the solution to be in L infinity. But remarkably, Vente proved that no, it is in L infinity. So Vente proved the following famous inequality. So let me call this phi. Let me call this dx and y. So his inequality is that this is so it doesn't have to be ux dot dy. It can be the Jacobian. It can be the Jacobian function. And the result is that this. Okay. So this is Vente's inequality. There's some subtle cancellation going on here. Because if you, as you saw with the Dirac mass, I mean, it's a false inequality, and this is one of the fundamental things he used in his existence theorem for constant mean curvature, and also then elaborated by Regis and Cohon in their solution of the Rayleigh problem, which you know very well what it is. That is, so here you have a sphere, so you take a curve like this, then there is a small solution. So you are trying to solve mean curvature equation with boundary value this. So there is a small solution here, which is the top cap. So this can be obtained as a minimizer and this was done by Hildebrand. And then there is a large solution, which is the bottom part. And there was a conjecture. There are two solutions. That's the Rayleigh conjecture, and this was done independently by Michael Struve and also by Regis Cohon. And later, in a general idea, using it falls out of a one bubble computation in a paper of Marchiotti. So we actually did the multi-bubble thing. So we got solutions with lots of bubbles, and if you look at our paper in the early section, we do the one bubble calculation and we cover all these old theorems as a byproduct. Okay. We are actually doing the most theory for the full bubble expansion, multi-bubbles. All right. So you see that there is a cancellation. I want to just make one tiny remark, and so I just want to point out a theorem with my colleague. And that is, you don't need, the Laplacian is not needed. You can actually take any divergence form equations in two variables, elliptic here. You just take two functions, okay? And there's no regularity on this, just bounded measure. Okay, so there is x1, x2, and then probably have this problem. X2, x1, so x is x1, x is x1, x2, okay? And so you take this less than mod psi square and bigger than lambda mod psi square. So you take anything like that, and we prove that you get okay. So it doesn't matter, there's no regularity assumption on it, just this, and you pick up the Vente result. And the key, the punchline of our paper is that we found that the Green's function of any such operator is in the John Nirenberg space BMO, with BMO norm only dependent on this uniformity constants. And it turns out that this part, the right-hand side, is in the Hardy space. This is a theorem of Kaufman, Dion, Mayer, and Sense. So if the Green's function is in BMO, the right-hand side is in Hardy space. Pfefferman's theorem says the dual of H1 is BMO, and therefore, by the duality, this falls out. So that was the key calculation. Okay. So having said that, let me now try to give you an idea how you are going to attempt this. So the point here is that there is a way of writing the right-hand side, taking into account the cancellation, and sort of it allows you not to take that many derivatives along the light cone. So there is a hidden cancellation going on, which is true with all these null forms. Because if you just write down some hyperbolic PDE, you're not going to go far. This is coming from some geometry. That was why we realized that this additional geometric cancellation information should allow you to go at least below the standard result. And already we see we are half a derivative underneath. Okay? So the point here is the following result. And so the fact. Okay, so I would like to say that the idea behind finding that, I would like to say that that we sort of suspected there is such a thing is actually because we were thinking also of some old work of Kahneman and Qatar in some other context. And so if you fool around with that, you end up with the following thing. So you take Qij, so just think, this is a system, but I'm just looking at one component, okay? So I look at Qij, phi psi, and this is a phi x1, psi x2, minus phi x2, psi x1. Okay? This is one component of the right side. Okay? So it's one of the components. So U is U1, U2, U3, and then you do this Jacobian. So the one component looks like this. Just write out the cross product. And this is what the cross product will look like. So it turns out that Qij of phi psi, and I will have to, and this is a key calculation. Okay? So this is, now I'll have to tell you what these objects are. So V half, V minus a half. So let me point out to you that V half is, we have seen this operator in the morning. This Alice had introduced this operator. So this is psi f hat. So this is a pure space derivative. This is a derivative purely in space. This one, d minus 1/2, so this is a psi tau, d minus 1/2 of f hat is equal to, and this is along the light cone. So this is differentiation along the light cone. So you have half a derivative in space, half a derivative in the light cone, and then you have here e 1/2 phi, e 1/2 psi. This guy is okay, but the horrible guy is this one, which is t 1/2, and this one goes inside. So and then the symmetric guy. So these two terms are actually pretty bad, and this is these two terms are the one that sort of really is preventing us from going down to H1. These two we cannot sort of handle. So you see here that you see what's happening here. In a sense, you see we are taking only half a derivative along the light cone. So there is that miraculous cancellation in proving this thing. I mean, if you try it with any other thing, it is because of the null structure. If you don't have the null structure, it's not going to work.
So in your Fourier transform, psi is along the space direction.
Pure space. Yeah, psi is the pure space direction.
But tau is the t direction.
Tau is the t direction. So you are differentiating along the light cone direction, but only to order 1/2. And this is, if you try to do it with some, you write down some function and you do it, you're not going to do it. It's because there's a null structure here. This cancellation, this is central to the whole thing. So then, you see, now I'm going to define for you the HS spaces. And somehow what you have to do here is you have to work with the algebra of HS.
So your QIJ is just this operator, QIJ component, right?
Well, QIJ is just one of these components.
Oh, you write QIJ?
Yeah, it's like a scale.
Yeah, okay.
You can. It's like, you see, U is U1, U2, U3. So you can think of the phi and this as a psi, for example, and you write the cross product, and the cross product is exactly that guy, right? And then if you look at the cross product and you look at cancellation, yeah, you have three such things. You have three such things.
Yeah,
each one you have to write it.
But why you need two in this?
Okay. I mean, there is an ij here. Maybe this is what you. Maybe I should write this as phi I, phi j. Maybe if you want.
Yeah, that's okay.
Like this. Oh, maybe it should. Okay. So ij goes from 1 to 3. All right. So let me define now the HS data spaces. Okay. So this is the space of U X P belonging to S prime Schwarz space, such that lambda S, lambda minus theta of U belongs to L2. So these are the analogs of those guys, except that you now put a 1 plus. So in other words, I'm saying here that this is equivalent to 1 plus mod psi square S over 2. So that's this guy. Okay, that's this operator.
So S prime is tempered distribution, right?
Yes. Okay. And this is tempered distribution, the dual of the Schwarz space. And now this one is exactly the same thing that I wrote down along the light cone. And here you have U hat some tau, and this belongs to L. So you see here that this thing is exactly the old thing here, except that now I've added. So the fundamental fact. So now I want to say a few things about. I mean, I cannot develop the theory of these Bourgain spaces and so on. Is that they have appeared now in many places by many mathematicians, especially principally Kleinerman and his colleagues, and also Terry Tau and of course Bourgain. So I cannot do full justice to it, but I would like to describe for you few of the properties and tell you a little bit how it gets utilized in our work. And I cannot tell you all the computations. I mean, by nature, as everybody in this theory complains, is that these things, the wave theory and all these things with general relativity and so on, they look very complicated and forces people to not to come there. But if you want to do something, you have to spend some time. There's no other way. Involve yourself, get into this and dirty your hands. All right. So there is a little lemma, and this is a very important lemma, because from this lemma, many of the fundamental embedding properties follow. So the way you should view this lemma is basically very simple. The way I view this lemma is that you can take functions and decompose them in plane waves. So it's a sort of decomposition into plane waves. So I will cheat a tiny bit in the proof. I will give you some proof, but I will cheat a tiny bit because we are running short of time. So you take a function, say u plus minus xt. So there is no real reason why I should write this u plus minus, but I could have done u plus and so on, but okay. So you take a function in space-time, and you can write this as 1 over 2 pi minus infinity to infinity. Okay? And here you have e to the I t. There is a parameter lambda plus b. B is that guy. B is that guy. So it is e to the. It is the the evolution operator e to the I t mod psi if you take the Fourier transform, and then you have a f lambda. Okay, and so there is a function x here. So this is really a function of x. Okay, and then you have e lambda, and then in the denominator you have 1 plus mod lambda delta. Okay. And it turns out that you can decompose, and the key point is that the HSB, H as theta norm of this thing in Rn plus 1 is equal to the L2 norm of U of this F of R valued in HS. So these two are the same. So essentially, many of the estimates for this you can translate to estimates on that, and then making the estimates on that you can relate the HS theta to various LP spaces. So you can make a link between LP spaces and HS spaces. And I will show you in some very simple examples how this can be done, and the trick is to use this thing. And this is very much intimately linked to the wave equation. It has been concocted keeping the wave equation in mind. So how do you do this decomposition? Okay, proof. Right. Proof. So here's my choice. So sorry, I said a plus minus. So the plus minus comes in there. So that's the plus minus. So it's the choice that you make here. The choice that you make here is the plus minus. Okay? Alright. So here's a select or set. So here you select f hat of lambda psi. So this is here, so this is a partial Fourier transform. So you're taking the Fourier transform in the x variable. That's what I'm saying. This partial Fourier transform is simply given to you as 1 plus mod lambda to the theta, and you see what normally you would expect. You restrict the Fourier transform of the function u to the light cone. So it's exactly what any harmonic analyst would do, right? Because of the Stein-Thomas restriction. So you have sort of moved away. I mean, you have added this lambda to the light cone. If you are on the light cone, then basically lambda is 0. Then you will be exactly on the light cone. All right. Now I claim that once you make this choice, then everything follows. Okay. So what's the proof? Proof is very elementary. Proof. So I shall prove this out here. So, all right. Maybe I should use that word. So, all right. So I take this and I take the Fourier transform in x. Take partial Fourier transform. So if I take the partial Fourier transform, then you see this is just a t integration. So if I do this t integration, then you see what will I get? I will get here 1 over 2 pi minus infinity to infinity e to the I t lambda plus mod psi, because remember the symbol of this is mod psi, and I'm just let's say I'm just working with the plus part. Forget the minus 1. And then I have to take the Fourier transform of this, but for the Fourier transform of this, I use that value. So I get here 1 plus lambda theta. I get u hat lambda plus psi. I get psi, and I get here d lambda. And here I get 1 plus lambda theta. So this cancels. Okay? And now I change variables. So I change variables and I say lambda plus mod psi tau. So if I do that change of variables, then essentially I'm going to get here t to the I tau. I'm going to get here u hat of tau psi d tau. Okay, so now I'm taking the inverse Fourier transform. So in tau, so this is going to be the inverse Fourier transform. So I'm still left with the Fourier transform inside, but I take the inverse Fourier transform. So let me put the psi here to denote that I still have the Fourier transform inside. And that is exactly equal to taking the partial Fourier transform in x. So I have the identity. So that shows that this is okay. Right? So this plane wave decomposition immediately allows you to manufacture many embedding theorems which are of great use. So let me show you a flavor of what sort of embedding theorems you can get. Typically, when you are proving these embedding theorems, so these embedding theorems are a combination of Sobolev in space and Strictheart in space-time. And then there are many such things. I mean, if you see the literature or books or some, not books, but you see the literature, you will see like the 20 inequalities in some papers of Feynman. Okay, so so let me skip this. I don't want to miss this. All right. So here's one. So we are going to basically always take theta together. Life is just easier if you take this. So here's one. So and that is that for theta bigger than 1/2, h as theta embeds into continuous functions valued in. So in other words, what do I have to do? I have to look at this. I have to take the hs norm of this function, supremum in time, and I have to control this by the hs norm of u. Okay. I hope this is completely clear what I have to do. So I'm going to compute the hs norm in part. No. Right? And then I have to take the supremum in that. And I have to control this by the hs norm, hsd norm, or hs theta norm of u. Okay, so I have this plane wave decomposition. Right? So I apply hs and move the hs thing inside. So for fixed t, just apply. I move the hs norm inside. So if I move the hs norm inside, then I just kill off the absolute values. Okay, so the absolute values and so on. You see, this is just the wave equation. So if you are e to the itd and you are in the hs norm is preserved by the wave equation. So in other words, what am I saying? I'm saying that this is the same as e to the itd f lambda hs norm d lambda 1 plus lambda theta. That's all I'm saying. This is nothing. It's just taking the absolute value inside. But you know that this is the wave equation and it preserves the hs norm here. So therefore, this is controlled by the hs norm of f. So this is controlled by the hs norm of f. And now it's very simple. Just take Cauchy-Schwarz. So if I take Cauchy-Schwarz, So I will get here. That's where it's used. And what is this? This is that. But this is exactly what this is about. So this is a sort of embedding theorem you can do. Okay? Now, if you combine this with Sobolev embedding, so if you combine what I have said with Sobolev embedding, you have the following result. So another proposition. Okay, I'm not going to prove this, but the result is that Hs theta embeds into L infinity of Rn plus 1, okay, when S is bigger than n over 2 and theta. This is a combination of Sobolev and the embedding theorem and the previous embedding. Okay.
What exactly is this F? This F is
I defined it. I erased it, it was somewhere. The U hat of lambda plus mod psi, comma psi, 1 plus mod lambda to the theta. That was the F. It was a Fourier transform.
Can you remind us where do you really use theta bigger than 1/2? Why is theta bigger than 1/2?
Theta bigger than 1/2. Because when you apply Cauchy-Schwarz, you get 2 theta. And that better be integrable.
That has to be bigger than 1 for your seem to hold, but you seem to skip that term anyway in your estimate.
Yeah, this is
So you
somewhat
want
true.
it to be integral.
Yes, so I get here d lambda 1 plus lambda to the 2 theta. And so if theta is bigger than 1/2, this term is integrable. Otherwise you cannot be. So when you apply Cauchy-Schwarz at this stage, here you apply. Alright, now a little bit more complicated is the following result. Okay, so you have many results of this type which are just using embedding and so on. But now a more complicated theorem is the following result, and this is a combination of the Strictheart's equation for wave equation and HSB spaces. And you remember why HSB spaces are important, because you saw last time that in the scale of HSB spaces you see a little gain of derivatives for box U, for the D'Alembert. If you are in the just pure Stricthearts, there is no gain in derivatives, it's just a gain in LP spaces. It's not good enough. Not for this sort of geometric type problems, it's not good enough. Maybe it's okay, I shouldn't say that. I should say that just using pure Stricthearts is good if you are working with Yamabe problems. You are working with Yamabe problems, semi-linear problems. That means you have seen all these Yamabe equations, except now you are out of the elliptic case. You put a UTT. You want to do all of this analysis there. Then you can get by with just Stricthearts. You don't need to get into HSB. But when you are trying to deal with these things like Yang-Mills or Maxwell-Klein-Gordon, or this funny thing that we are now looking at, which we introduced, there is no hope. If you just, there is no hope means there are no good Stricthearts estimates, and the Stricthearts estimates have to be put along with something else. It's not good enough. Okay, so here is another one. So before that, let me go back a step and tell you what is a Stricthearts estimate. And eventually, the last part of this lecture, I'm probably going to tell you what a Stricthearts estimate, how a Stricthearts estimate can be derived. What is it you need to derive a Stricthearts estimate? What is a Stricthearts estimate? Now we have all these Stricthearts estimates. All Stricthearts estimates have 2 components. Once you have these 2 components, a machine takes over. That's what it is. Yeah. There are many people who do many Stricthearts estimates, but there are 2 central things you need. Once you have those 2 central things, you are in business. Okay. So this is a Stricthearts estimate, and I'm not going to prove it for this one. This is for the wave equation. the Strictheart estimate I will prove will be for the Schrodinger, the one that Kirill wrote down in the last talk. So it is that one I will prove, because there are many technicalities and don't appear there. In the wave equation, there are a lot more technicalities. Okay, so you have D'Alembert u equal to 0. Let's say this is one form. U of x0 is f. Ut of x0 is 0. So very elementary Strictheart estimate, or the very basic one. Then for 2 less than q less than infinity, 2 less equal to r less than infinity. So I want to point out that this equality, this case of equality, this sharp result is due to Terry-Tau and P. So this is a paper in the American Journal, and here you take S. So there are all sorts of indices, and there are reasons for these indices. So this is just scaling. This comes out of just scaling. And then you also have what is called the wave compatibility condition. So this is 2 over 2 less than or equal to n minus 1 over 1 half of this 1 over r. This is called wave compatibility. Condition. So I'm not going to. So you have a similar result. So this is not the one that's actually Strictheart wrote down, but it is a much more general version. And then you have the LQ norm in time, the R norm in X is controlled by constant times the HS in Rn. So this is space-time in the data. Okay, and so in the special case, so here there are some restrictions you will see. When S is 1, okay, you get Q equals 2, you have R equal to 2n n minus 3. And here, of course, we need n. So this is a special situation that when S is 1, and you take Q to be 2, then R has to be taken by this. You work your way through this by plugging in these values here, and you see what this is. So, so this is the Strictheart estimate. Unfortunately, as you are seeing here, things like this do not apply for us because we are in dimension. So if you use this Strictheart estimate,
So the notation that you take
the LR norm in space,
and then you integrate on T LQ.
exactly. So these are called the mixed norm or space-time norm. Strictheart actually did Q equals R. This was Strictheart's case.
And then
look at it,
your box in the standard of the
D'Alembert. I mean, you can do it on. There are problems to do it on Riemannian manifolds and so on. I mean, one should not think, these are estimates. You're not going to get a Strictheart estimate on the sphere because you are bouncing around in the geodesics. There is no dispersion. The geometry of the Riemannian manifold is crucial for these things. You try to prove Strictheart's estimate where you have closed geodesics or trapped geodesics, you're going to die. You're going to immediately run into KM theory. Okay? I mean, this is some Francois and I tried. We started getting number theory. That time I gave up. Because you have to look at closed geodesics.
Yeah, that's very interesting. Yeah.
That's why Bourgain is successful. Because he knows a lot of number theory. Alright. There is, however, a paper of mine in some proceedings of the Indian Math Society I wrote when D.B. Tiwari retired. And there I actually have a Strictheart estimate on semi-simple regions for what are called pi invariant functions. It's the only place I know where somebody has done something for pi invariant functions. and I wrote down a Strictheart's estimate. But there has been some work by French people for hyperbolic space. But in that general context of G mod K, G complex, I was only assuming G mod K, G complex, and I have Strictheart's estimate. It's a little paper. UB Theory was retiring and I needed to write something. I don't know whether you know this person, but he was my teacher in the old days. Long time. Oh. Okay. So, if I use this sort of result, then I shall be able to prove the following here. And I can do this, leave it as an exercise. And the result is that H1 theta embeds into L2 of t, Lx of 2n by n minus 3, when n is bigger or equal to 4, theta is bigger than n. So this is a direct consequence of the Strictheart systems. And the proof is very simple actually, if you know this. So this special case, if you take this special case and couple it with that plane wave decomposition, then this follows. And the idea here is you have your u x t, and then you have whatever minus infinity to infinity, you have e to the I t plus or t, and then you have f of lambda, and then you have, this is in x here, g lambda, and 1 plus mod lambda theta. So again you see here that now if I were to, so you see what I do is I write this as e to the I t lambda, and then I write this as e to the I t b of f of lambda, and I write this as 1 plus lambda to the theta b lambda. Break it up. So what is this? Well, this is the solution to the wave equation with the data in f lambda at time 0. Right? I remind you, those of you who have not seen this, let me remind you that there is some amount of cheating there. Usually it is cosine or something, but let's forget this cosine. So if you have a wave equation and u of 0 is there, okay, then essentially on the Fourier transform side, you have a e side. So this is just a partial Fourier transform. This is roughly given by e to the I t mod square. This is the solution of the initial value problem. Okay, so if you see that here, you see that exactly here. This is the solution of the initial value problem, where for every lambda is fixed, and for fixed lambda, you are solving the initial value problem. So if you take the space-time norm here, you can pass the space-time norm here and apply Strictheart's. So when you apply Strictheart's here, in that space-time norm, this will immediately take you to the H1 norm of f lambda. And then you apply Cauchy-Schwarz, and you can relate the H1 norm square L2, you can relate it back to the HS spaces. This is the idea of it. Okay, so the idea is apply, so on this piece, you apply and then fall down. So there's a whole list of things here, and you can do it with not just s equals 1, you can do it with the arbitrary fractional s and so on. I'm just selecting one special situation. But you can see here that there is a combination of space-time norms being controlled in terms of this. So you see, this sort of thing. So this sort of thing has been transformed into this sort of situation, and this is what Kleinemann and company call the transfer principle. So any type of space-time estimate of this form gets transferred to an estimate or an embedding in the HSP spaces. So there is a natural transference. And now the situation gets even harder because then you have to also now start to think of what doing this when in a bilinear setup. Nonlinear problems, they are bilinear situations. So that is where things start to get hard. You have to use a lot of harmonic analysis to deal with this.
So here the inequality C will depend upon T, or C is independent of T?
Which? This is global. Independent of F and C and now otherwise it's of no use. It will depend on T. I mean you are integrating out in T, so how can this depend on T? There's an integration here in T. So how could this depend on T?
So this is for unity or T?
No, it's global in Rn. This is Rn. This is R plus Rn. In space time. You will see. I will prove the Strictheart for you. Then you will see what are the ingredients in these. You see, there are two rules in the game. Okay? The simple thing is that you don't prove a Strictheart inequality, you cannot use. Because otherwise you have 1,000 Strictheart inequality. You only prove a Strictheart inequality which you need for a PDE problem. That's the first rule. The most cardinal rule. Otherwise, there are many people write many articles on Strictheart estimation. They don't have any value. So you prove what you need. Because there are many possibilities of the mixtures of norms you can get. You can put a best of norm here, this norm here, that norm here, this sort of thing. You can make best of norm here. Okay. You take some books, they are doing best of space. So whatever is needed for a problem, you use it. Otherwise, there are huge zoo there. Okay, so all right. So the idea here is let's go back here. So I unfortunately have erased this thing. So let me just go back and let me tell you the punchline that I need for my work. So what we do is we are, so Jurgen's question is that we actually get existence in HS theta spaces for S bigger than 3/2 and theta bigger than 1. It is here we are getting the existence, in this space. Okay. So, you have this object which is B 1/2, B minus 1/2, B 1/2 phi, 1/2 psi, and plus B 1/2, B minus 1/2, B 1/2 phi, B 1/2 psi, and there is some. Okay, so suppose you know phi, psi are in HSB. So this thing is now going to be in HS minus 1/2 of theta, and this thing is going to be in HS minus 1/2 theta, because you lowered the derivative here by 1/2. So the first question that you have to answer is what to do when you multiply two such functions. Where will you be? Because this is what exactly you are faced with. So that is one of the lemmas. Okay. So there you have to be careful because some of these things are well known, but known in some higher dimensions and so on and so forth. You have to be careful to see which of these things are valid in dimension 2. We have to be careful here. So the first fact, so lemma A is that HS minus 1/2 theta dot HS minus 1/2 theta is going to go to HS minus 1/2 theta if S is bigger than 3/2 and theta bigger than 1. So that is one of the ingredients. Now this term is actually worse. So here, this is going to be in H, look what happens here. You differentiated 1/2. So you have S minus 1/2, and now you differentiated here in 1/2, so this becomes theta minus 1/2. You lowered the theta here, and this is in H minus 1/2 of theta, because you just did a space differentiation. So you need to know what happens when you multiply these. And so that is the content of the next lemma, the next part of the lemma. Okay, so that is HS minus 1/2, theta minus 1/2, hs minus 1/2 theta goes into hs minus 1/2. So you cannot take this. I mean, you have to be careful here because somehow the fact here theta is bigger than 1/2 is used here. You cannot lower the theta. And this is the one that this term is the one that is sort of preventing us in lowering the thing down to h1. There is a hope that we can work with h5/4, maybe lower down a quarter.
So this only happens when S is equal to 3 half.
Yes, that is this algebra that we could not establish this for S lower than 3. If we can do something, it's probably false. That feeling this cannot be true. You have to work with maybe a subspace of hs theta, which is what these huge papers in JAMS or Pleinman they work in a subspace. So you have to intersect hs with something. Maybe this machine can take us down some, but I'm not. I mean, I think h1 is hard, energy critical. That probably is work. So here you see that the idea. This is the key idea that we have to use. So this is decomposition, and then in these things we have all of these products, and then you have to understand how to multiply two HSB functions, appropriate indices, and then you control it like I showed you in the slides. You have a control on the null form in terms close the estimate. Then if you close the estimate, then you are in a position that lies in this form, whatever you do. Okay, so now I have 45 minutes left. Hopefully, I'm going to finish even earlier. Most of you will be very tired. I want to present to you a proof of a Strictheart estimate in a very simple case. So we have heard this several times, and I'm sure some of you are very curious how do you prove such experiments. So there are two essential ideas in proving a Strictheart estimate. Okay, so let me explain to you. Point out to you what is the Strictheart estimate I will prove, and then point out to you how do you prove such an estimate. Okay, so I'm going to look at I ut equals Laplacian of u. Okay, so this is an R cross Rn. Okay, so Ex, and I have. Oh, so I will even take an F. I will take inhomogeneous. I will take inhomogeneous, and I'm going to take, let me look at the notation. Yeah. So this is, I have no derivatives, this is a first order derivative, so this is my question. So what do I mean by a Strictheart inequality? So the Strictheart inequality that I have is the following. Yes. So I want to prove the following. So I want to prove a very simple-minded one. So I'm going to show that u of xt, okay, in LP or in LQ. So we know specifically it's the way I've written it is Rn R plus, which is Rn. Is bounded by the L2 norm of H. This is the data plus the LP norm in Rn R plus. Okay, and my Q is related to the P like this. I mean, after all, these are like Fourier transform. So we know from the workshop there was this Hausdorff-Young inequality. So basically, all these wave equations are like Fourier integral operators. So if you have a Fourier integral operator, basically at a naive level, it must work like the Fourier transform. And for the Fourier transform, we have Hausdorff-Young, which says LP goes to LP prime. So this is not surprising, highly not surprising. And the P value can, however, not be anything. It is, as you saw in the last talk, 2n by 2 over n plus 4. I think Kirill wrote the Q value, and here I'm writing the P value, and he wrote it as 10 over 7 or 10 over 3 when n is 3. And here you will see you get 10 over 7 because that is the value on this side, and he was writing the value there. So there is this relation. So this is 10 over 3, this better be 10. So how do you prove such an estimate? So I want to show you a complete proof.
So it only holds for this particular L, P, and Q.
Exactly. So you are forced to. That is why people have to do this mixed norm estimate. That gives you more room. See, if you follow my proof, you can recover the fixed norm estimate. That's an exercise. I'm just doing it in this special case because I don't want to lose you. But you can take my proof, go home and worry with the mixed norm estimates you will get. You may not get the maybe some endpoint, but you will get the entire mixed norm estimate. That is why these mixed norm estimates were introduced, because it gives you more flexibility in this problem. And the second point I want to point out is because you see my training is from harmonic analysis. I want to point out that every Strictheart estimate is equivalent to what is called a Fourier transform restriction theorem. That is not the way Strictheart proved it. He first proved the restriction theorem and then the estimate. I am saying I want to first prove the estimate and get the restriction theorem as a corollary. You can go any way you want. You can go, if you know a restriction theorem, it means a Strictheart. If you have a Strictheart, it's a restriction theorem. That's what I want to say. The equivalent problem. Okay. So the most famous of this is the Stein-Thomas restriction theorem, and you know how important that is in unique continuation and inverse problems. And 1,000 other things, and some of you have articles that I've written up in the past on inverse questions, and you saw how the Stein-Thomas restriction gets applied in this unique continuation. So they all stem from harmonic analysis as practice in the 70s. So when the 80s came along, all these theorems were done, so we people who followed became users of this, because we had some PE background. We knew the harmonic. You could apply with all these things. Okay. So what are the two things you need? So the two things you need. So there are two things that prove that every Strictheart estimate utilizes. One, energy conservation. The second thing, you need a dispersive estimate. That means, you see, that as time goes forward, your solution decays. And that you don't have on the sphere. See, if you're on the sphere, you come back, and you'll never have a decay of the solution. And the waves have nowhere to move. I mean, you're trapped on the geodesics. That's why, you can't have, that's why it's very difficult to prove Strictheart estimates on compact manifolds. Geodesics keep going back. So that's why, all the Strictheart estimates, if you're hyperbolic, you're very happy, the geodesics go out like that. That's why, I could do it on G mod K, non-compact. I knew there will not be problems, so you can do it. Okay, so these are the two ingredients. So these two ingredients are going to be used in proving this. And you will see that they are fundamental. It's very clear in this proof how these things appear. It's very clean in this setup for the Schrodinger. Okay. Also, this wave compatibility and so on that I wrote down, this becomes equality. In the Schrodinger, this becomes equality. You don't get a zone. You can draw a picture here of 1 over R and 1 over Q. There's a big zone here for the wave. For Schrodinger, it's a straight line. So I will not get into why it is that, so on and so forth. So there are a few things I will not prove, but I think that what I'm going to leave are very elementary. And if you have not seen that, it would be very good if you try to find the proof by yourself. Okay, so what is it that is easy to do? All right, so firstly, what I'm going to sort of leave out, give a small sketch, is the Duhamel. So there is this operator KT. Okay, so this is the Cauchy this is the fundamental solution. So it is some Cn e to the minus mod x squared over 4t divided by e to the n. It's basically like the heat equation, then you just put an I there. That's what it is. And it's a fundamental fact Okay, it's a fundamental fact that. So I go here. So it is a fundamental fact that you can write down the solution here in the following way. So it is a fact that you can write down u of xt as kt convolved with h plus 0 to t kt minus s f of x s ds. This is called Duhamel's principle. So it's very simple to check this. What you do is just take the Fourier transform and then you solve linear first order ODE by the method of integrating factors, which you learn as the first method of solving any ODE, and then you inverse Fourier transform. And this is the initial condition. So you are going to see this. And if you have not seen it, then it's a good exercise to actually check why this sort of thing is. This is given in any standard PDE book. You take any standard PDE book, you will have it. Okay. So I'm going to first focus on this part. I will first focus on this part, and then I will get the estimates for this part. Because you can use superposition. You can assume that your u, you can assume here your h is 0, and then do it, and then you can take your f to be 0, and with the h, and then take the u1 and the u2, and take u1 plus u2. Because it's a linear problem, so you can use superposition. Okay, so how do I get the estimates for this one? And there you will see the two principles at work. Okay. All right. So what I do is I look at this operator, P of x. Okay. So it is equal to kt convolved. And I make two types of estimates. And the first estimate is the energy conservation, and the second estimate is the dispersive estimate. Okay, so what is the dispersive estimate? So let me write this guy down. So it is e to the I x minus y squared over 4t and e to the n over 2 dy dy. This is clear. So you see already that if I take the absolute value of this is bounded by 1 over t to the n over 2. There's your dispersive estimate. It's already telling you that this solution in L infinity, so you are getting one estimate, which is e of L infinity is c e to the n over 2 times the L1 bound. Just take the absolute value inside. The crudest estimate you can do. So this is what is called the dispersive estimate. You see here that as time goes to infinity, this right hand side goes to 0. Okay. So the next estimate is the L2 estimate, which is energy conservation. Next estimate is that actually Pg of L2 is equal to here. This is energy conservation.
Called mass conservation.
Sorry?
Mass conservation.
Sorry?
Mass conservation. It's called mass conservation.
We may call it mass or whatever. Yeah, but yesterday I was also calling energy is conserved for the wave equations. So it's a term now. Let's not get okay. So there are many ways to prove this. One way is through the Fourier transform. So if I take the Fourier transform of this right hand side, okay, so this is e to the I e mod psi square t hat square. This is the Fourier transform because that's the fundamental solution. The fundamental solution kt has a Fourier transform to the I t hat square. And the absolute value of this is 1. Therefore, this is equal to mod t hat square. Or if you don't like Fourier transform, then you can also do it by integration by parts. Multiply the equation by u, the Schrodinger equation, integrate by parts, and then you see that it's conserved by taking the real part. Okay. So now you see we have these two estimates. We have this one, okay, A and B. And the Strictheart estimate is just mediating between A and B. It's like a little bit of A, a little bit of B. That's what it is. And you see, the reason is the following. See, when you are dealing with nonlinear equations, you have to multiply functions. When you multiply functions, you are out of LP spaces, L2 spaces. You are forced to deal with LP spaces. And that is why you use Strictheart estimate, because you see your products of functions in nonlinear problems. Therefore, the LP type results are far superior than taking just a pure L2 or a pure L1. So if you mediate between the two, you arrive at LP estimates. And LP estimates are therefore much more superior when dealing with nonlinear problems. That was the whole focus of most of these workshops. I mean, you ran into e to the u square for all of these geometric problems. Okay? So you cannot hope to live in the paradise of L2 when you do nonlinear theory. You're forced to jump out of it. Okay, so what do you do next? Well, you have an LP estimate, L1 estimate, and L2 estimate. You want an LP estimate to interpolate, because nobody really knows too much about LP spaces. You know everything about it. I mean, this is our content of my workshop lectures. You remember we wanted to get singular integral estimates. We could do L2, we could do L1, and we didn't have any method other than interpolation. So we used it. It's very hard to do LP theory. It's very easy to do L2 because of what? You can use Hilbert space techniques. Kotlar lemma. One of the things we use.
So what level?
Kotlar.
What is Kotlar?
You're coming back to Raptors, right?
Yeah, okay, you
I'll tell you. You can come whenever. First week of class. I'll tell you. Okay. So now we interpolate and we end up getting KT involved with T. Okay? L2. Okay, the relation is 1 over P plus 1 over Q is 1, and this is by race theory. And then we come to the last trick in a Strictheart estimate. What is the last trick? The last trick is you always slice and handle the problem. You do it for one fixed x and then do the time integration. That is why you see all these space-time estimates. Okay, so now that we are here, I think we can put everything together and we are done with the first part. The second part is a nice trick, and it needs a little bit of work. It reduces to this problem. Okay, so here we go. Alright, so here we have this term 0 to P, K of P minus S, involved with F of X, S, P, S. This was what we had to estimate, right, in the Duhamel term. And so let me call this UXT. Okay? So let me take the LQ norm in fixed T. So fixed T and take the LQ norm. T is fixed. So take the absolute value inside. Okay. Now I use my theorem there. So this is bounded by, once I do that, I just ignore this. Just go all the way, just increase everything. So I get here P minus S. I get here N over 1 minus P of the LQ norm in Rn is. Okay? But now this should remind you of something from the summer school. Hard Hardy Littlewood Soberlab fractional integration. You are in fantastic shape to use it. You see the idea? You have kept one time and you sliced it, and then you use this interpolation, and now you're just going to do the t integration at the very end. And if you think of this as a function s. So I'm just putting it back into the language of our workshop, if you like. Okay. So call this hs or ht. Call this ht. So what do you have? You have ht less than rn r s over t minus s n over 1 over p minus 1 over 2. Yes, this is something I alpha of p in one variable. Okay. So now you want to take what norm of this? You want to take the same LQ norm, because you raise this to the LQ, the x is fine, and so all you have to do now is question when is h LQ of r less than c phi of LP of r. This is the question, because the LP norm of phi is exactly this quantity. Sorry, not L.
No, this Q is
This is Q and this is. Sorry, this is. Yes, this is P. So this is what we want to do. And so the question is that there is a formula which says that 1 over Q is equal to 1 over P minus alpha over n if you have convolution by So if you have convolution by this kernel, then you have 1 over Q equals 1 over P minus alpha. And you know what this alpha is from here. You can read off. So you can write this as 1 minus alpha, right? And for this 1 minus alpha, you solve for alpha, you plug the value of alpha in here, you do the algebra, and exactly it will come out to be 2 over n plus 2 over n plus 2. N plus 2. So I'll leave the algebraic manipulation and calculation.
Is that called a Ritz transform?
It's called Ritz potential.
Ritz potential.
It's like Green's function. So this is the end of the proof. So I have 5 minutes, and I could do it there. There's notes here, but maybe I just I think people are very tired. I would like to have done the H part, which was the initial data. That problem is turned into this problem by a duality trick. It's known as the Thomas duality trick. Peter Thomas was the person who discovered this trick for the case of the sphere. You use that and you can reduce that problem to this. And then there is a small trick that tells you that such problems are equivalent to what I call Fourier transform history. I would rather not do that now. It's already 5. I'm sure it's.
Okay, so best S you expect. Your S now is greater than
3 halves.
But
We expect 1. I mean, I don't see any reason why it should not be. It would be really bizarre if we don't get it at 1. But I think that it's very hard. I mean, this technology of HSB takes you up to 3 at the moment. Now you may have to take a subspace of HSB, which they call XS space or whatever, and maybe fool around with that. And then I think if you want to go down, you may have to do actually a little bit maybe frequency cutoff. That's going to be hard. Actually, we first did frequency a little bit baby, and we got it down to 7/4 using standard LP spaces. And then I think we realized that maybe we should try this thing. So if you forget the standard LP spaces and you work in HSB, it went down to 3 halves. So now we are 1/2 derivative. Once you do that, then we can start doing all the questions that people ask in the, well, then you know what will happen. I mean, you are going to solve, and then you're going to get H1 estimates when you're below 8 pi, and then you can solve, just like what happened for the Gauss curvature equation. That elliptic theory will come into play. But to start, you need full-fledged hyperbolic thinking. Once we get going, then elliptic technology will come.
Thank you again. I will do the dual duty since our dean is not here. I would like to thank all the visitors who have given wonderful lectures here on behalf of the Data Institute of Fundamental Research. I would also like to thank the National Center for Mathematics for the support it has extended to hold this conference. I thank all the outstation participants who have come here. Without participants, it's no meaning to have. I hope you have enjoyed your stay and the lectures, more importantly. And I look forward to having all three of you back at our center. And as it progresses, we have lots of young students who will take a lot of interest. They have shown a lot of interest. I look forward to your cooperation in developing these areas at the center. I thank you very much for the visit and the excellent lectures. And finally, thanks Tarun. We have been discussing this school for almost 2 years now, and I hope you have not been let down at the level of the students who have taken. Yes, there is some kind of, but still we have got the best of students from across the country to attend. I hope they have benefited not only from this school and the one we had in July. Good luck to all of you. Thank you again for coming.
Thank you.